Okay, so we're going to continue our study of graph algorithms, and we're also going to look at a general design pattern called greedy algorithms. So we'll look at this design pattern specifically applied to graph problems, but the concept of a greedy algorithm doesn't apply to just graph problems. It's just kind of a general approach for certain optimization problems where you're trying to maximize or minimize something. And we'll use it in the context of a few graph problems, but we'll also, in class, look at how it can be used in other sorts of problems. Okay, so the first example problem is the concept of a spanning tree. So we'll want to span a graph. So by spanning a graph, this is an example of a common real-world problem. The basic context is that you want to somehow connect together multiple cities. So I'm going to use an example of connecting together multiple cities with power lines. So a lot of my graduate work was related to power transmission systems, the large power lines that carry power across the country. And there are lots of challenging problems when constructing a big power system. One of the main ones is that power lines are very, very expensive to build. The raw materials are a little bit expensive, but the actual construction and getting rights to land and things like that are also a huge barrier. Okay, so this particular problem isn't quite the single source shortest path problem. So there isn't exactly a single source in a lot of these types of problems. So there are lots of different places that use power and generate power spread out across a power system. And we aren't exactly concerned about the concept of shortest path typically as we looked at with Dijkstra's algorithm. Okay, so different sort of problem. Okay, this can apply to lots of other things. I'm going to apply it primarily to the concept of a power system, but it could apply to any sort of a network that transports things. So data networks transport data from sources to consumers, oil pipelines, water supply, natural gas, wastewater going back to a treatment plant. These are all examples where this applies, and there are certainly other examples. These are all kind of concrete, physical, real-world examples. Our overall goal in this sort of a problem is typically to minimize cost. Now, there are other constraints, like in a power system, you also want to be sure you can deliver power with a certain level of quality. Maybe you want to have power delivery to be 99.9% reliable. So there are often other constraints in real-world problems, but we're going to focus on the pure, simple problem of minimizing the overall cost of the graph. Of the connections between all the cities. So we're going to start off with kind of an ad hoc approach. So we're going to start off with this example of a power line problem. So we'll have cities. Okay, so here's the updated graph. So this is very similar to our flight graph. I'm still using airport codes to indicate the names of cities. But now the edges represent the costs of building power lines, transmission lines between these different cities. Now, it's unlikely that we would actually build a transmission line that goes from San Francisco to Boston, but this gives us an idea of how this approach is going to work and is representative of actual real-world problems. So I have added a few different edges to this graph, and I have changed the weights just a little bit. Okay, so let's go ahead and start. So again, I don't really think it matters which city we start from because we have to connect everything together. So I'm going to go ahead and as I work through cities, I'll underline them. And as I select power lines, I'll also do kind of a dashed colored line along the line. So if I start at San Francisco, I want to build these lines as cheaply as possible. So I've got these 4 different options. Oh gosh, so that would be $2.5 billion. That's kind of pricey. 300 million sounds good to me. So we'll take the minimum of our available options. Okay, now I've expanded out to 2 different cities. Now I've got lots more options. I've got a power line that goes from LA to Miami, LA to Dallas, San Francisco to Dallas, and so on. So it looks like I've got a total of 5 different options at this point. Now, if I'm looking for my minimum value, it looks like I've got 2 options that are $1,100, or 1.1 billion, sorry. So I'm going to go ahead and, pick one of those. I don't think it really matters which one I pick, so I'll just go ahead and pick this one and go to Dallas. So now I've expanded out further, and I've got kind of this group of 3 different vertices and all of the outgoing edges from all of those vertices. So 2,500, 1,800, 1,100, 800, 1,400, 1,100, 2,300. Okay, the minimum of all of those is this one up here that goes up to Chicago. Okay, and again, we just repeat the process. We look at all of the available outgoing edges from the cities that we have already made a path to, and we select the minimum. So once again, I've got kind of an arbitrary choice. I've got 2 things that are 600. So I'm just going to go ahead and arbitrarily pick this one. So that goes to New York. Okay, so at this point, I pick my minimums. Again, I've got two that are 200, kind of arbitrary. So I'll go ahead and pick this one going up to Boston. Now if I look at all my outgoing edges from all of the cities that I currently have available to me, I've got this one down here that's 200. So we'll go ahead and build that one out. And now if I look at all my outgoing edges, I've got this one, 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 and that one. Oh, my minimum one is this one, the one that goes from Chicago to Boston. It's 700 million. But I've already connected up to Boston. It's already in my network. So I don't need to build this because I've already got a path that I could use to transport power. It may go the long way around, but for things like power, that doesn't really matter too much. We'll assume it doesn't matter at all for these types of problems. So I'm going to go ahead and ignore that one. So I'll just kind of cross it off. And then I'll look at my next lowest value. So it looks like my next lowest one is this one, which goes down to Miami. So at this point, everything is connected together. Okay, so a couple of things. When we're all done here, we have some overall cost, and it looks like we made several arbitrary decisions. There were several cases where we had a couple of choices that were equal value, and I just arbitrarily picked one. So first of all, let's think about our overall cost. So our overall cost is the sum of all of these. So 300 plus 1100 plus 800 plus 600 plus 200 plus 200 plus 900. Okay, and so that's going to give us some overall total, which looks like it's 4,100 or $4.1 billion. So kind of pricey. So in just a second, we'll kind of review this, but this is a minimum value. We'll find out soon that there might be multiple ways to achieve this, but this specific number, the total that we get, is in fact unique. Okay, so a couple of other things to note here. I stopped when I had connected to all of my cities. So basically I could use the number of vertices as kind of as the stopping condition. When I'd used all vertices, I was able to stop. This type of problem only makes sense if there is a path to every vertice. So if our graph had kind of two disconnected sets of subcomponents, this algorithm wouldn't have worked. There just wouldn't have been a way to connect everything. Also, the total number of edges that we're going to have is essentially the number of vertices minus 1. That gives us enough edges to connect everything together. Okay, so I want to rework this problem, but there were two places where we had kind of arbitrary decisions. So just as kind of a proof of concept, I'm going to focus on these two places where we had arbitrary decisions. At some point, we could choose between these two paths of 1.1 billion or these two paths of 600 million. So I want to redo the problem, but I'll make different decisions in each of those cases, and then we'll just look at our overall total when we're done. Okay, so starting over. So just like before, I'm going to choose my same start city, and I really only have one viable choice out of here, the path to LA. Now I've got these two different decisions. I'm going to go ahead and go with this path instead of the one that we chose last time. So I had the two choices that are both 1.1 billion. That gets us as far as Dallas. So then I've got several different outgoing edges, this one and 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 this one. So just like before, we actually end up choosing the same path that has a total cost of 800 million. Now we've got several different outgoing edges to consider again, 700, 2500, 1800, and so on and so forth. We are down to the same two minimum values of 600 million. So before we chose the path to New York, this time we'll choose the path down to Baltimore. Okay, at this point, if I consider all my outgoing edges, I have this path of 200 to choose from. And if I repeat the process somewhat like before, I have this path of 200 to choose from. And now I've got several different choices. I've got this minimum value of 700, which again, it connects to something that we're already connected to, so we'll ignore it. And now I've got this, my next minimum is the 900. I've gotten through all of my vertices, so I'm done. Okay, so we've got a slightly different graph. So last time we used this edge, and this time we've substituted two other edges. That idea of substituting or exchanging edges is something that we're going to see a couple of times, and it will be useful to us as we're constructing proofs of greedy algorithms. Okay, so we substituted one edge with a value of 1100 for another edge of a value of 1100, and we substituted one with a value of 600 for another of 600. If I substitute these differences into my overall total, my overall path cost, I'm going to end up with the exact same cost. I've traded something for something that's exactly equivalent. But my overall network, the overall connections are slightly different. Okay, this overall result that we've achieved here is referred to as a spanning tree. So I'm just going to quickly redraw this and essentially have the same information in my graph. I'm just going to draw it out as a slightly different layout on paper so it looks more familiar to us. So I'm going to start with SFO, just like we've been doing, and it looks like we've connected to LAX and DFW. And I could, of course, keep all of my edge weights here. Let's see, and then Dallas is connected up to O'Hare with a path cost of 800. And scooting across my graph, now from O'Hare, we've got a path of 600 to UI. And then from there, we've got both JFK and Miami. And the corresponding weight costs of 200 and 900. And then from JFK, we've got Boston. Okay, so you can see this is basically a tree. Now, it's not a binary tree. Sometimes there's a single branch, and it would certainly be possible to have 2 or 3 branches. It is kind of a multi-way tree. And when we think of these sorts of spanning trees, there isn't a distinct route. I've drawn it considering the route or the starting point to be San Francisco, but I could have chosen any of these nodes to kind of be the route. The basic idea here is that overall, this has a very similar structure to the trees we've been looking at. It's connected. There is kind of the concept of a branching factor going out from a particular node. Okay, so we've constructed this spanning tree thing. So it spanned all of the vertices in our graph. Specifically, we were going for this idea of a minimal spanning tree. So it minimizes the sum of edge weights. Okay, so let's be just a little bit more formal with this concept. So we've got some graph G that's composed of edges and vertices, and we've got some function W that gives us the weight of a particular edge. So this is just a more formal way of describing the edge weights. So our goal here is to pick a set of edges T that achieves 2 things. The graph is spanned, so there's a path between all vertices. And our second constraint is that we want to minimize the overall cost involved. So we want to minimize the sum of all these weights. So kind of formally, capital W of the set T will be the sum of all of the edge weights in T. And our goal is to minimize that, to have that achieve that unique minimum value. So overall observations, there is some unique minimum value. There may be multiple valid sets of edges that achieve that. So the set T that we've been talking about isn't necessarily unique. There could be several things that achieve the same minimum value. We can make equivalent exchanges of the edges used to transform from one of these valid solutions to another. Another subtle thing is there won't be any cycles. A cycle would imply going back to some place that's already connected in the graph. The edge weight that would be added on would increase our cost unnecessarily. Okay, just continuing to be formal, we'll take a quick look at the Wikipedia article on spanning trees. So a spanning tree is a tree, specifically they start discussing undirected graph, but also the article goes on to discuss directed graphs. So it's a subgraph. It uses a subset of the vertices and edges. It uses all of the vertices, but it may not use all of the edges. So it has a minimum possible number of edges. So that's just the generic idea of a spanning tree. The minimum spanning tree, as we've already discussed, minimizes the weight of the edges. So sometimes it's just referred to as an MST, minimum spanning tree. Also, there are several different algorithms. So there's a whole section on classic algorithms and faster algorithms that can be used for spanning trees. So we'll look at two of the classic algorithms that use slightly different approaches. One of them is essentially the ad hoc approach that we've just used.